So today, I think the last probably that we'll talk about standardization for causal inference. We've been talking about it for a while. I do think it's one of the most important things that you can do with regression in public health. So I think it makes sense to spend time on it until you're comfortable. Today, we'll talk about, in particular, how to get subgroup effects using standardization, and also effects of treatment on the treated, which is another type of effect that people are sometimes interested in, other than the average treatment effect. I had a paper recently that's just basically doing exactly this. It's just like linear regression and standardization and subgroup effects. So I'll just show you that as another example of finished product stuff that you can do. And then we'll also talk some more about when is it safe to do causal inference and what do you need to adjust for to make sure that exchangeability holds and you can interpret your results causally. I tiptoed around describing what the assumptions are because it's not really the focus of the class. You'll learn about this in EPI later, but I figured you might as well learn it twice. It won't take too long to describe the no backdoor paths criterion for knowing exactly what you need to adjust for from a causal graph. Then I'll try to make you guys better consumers of regressions and know when to be skeptical of overinterpretations of regression coefficients. And then we'll see multivariate regression for analyzing data from randomized trials. We've been talking about observational studies, but you can actually also use regression to analyze randomized trial data. So first, let's start with subgroup effects and the effect of treatment on the treated using standardization. What is a subgroup effect? It's the average effect, the difference in that outcome had you been treated minus had you not been treated, among people who have some value of the covariates, or it could just be a single covariate that you're restricting to, some subpopulation. That's what given x equals x means. So an example is, what is the effect of quitting smoking on weight gain in that NHAFS data set that we did lab 4 in? We looked at the effect of quitting smoking on weight gain in a general population. You could say, let's restrict to the subgroup of men in that data set and see what the effect is in them. This is pretty simple to implement. You just need to restrict to the subgroup of interest. So in this example, men, when standardizing. So when you estimate the outcomes under each treatment, you just do that in the men and take the mean just among men, and then take the difference. We'll go over an example. And then the special case of a subgroup effect is the effect of treatment in the treated. I think it was Emily last week who was asking about interpreting effect estimates and asked if it was the effect in people who received the treatment. And the average treatment effect isn't. That's the effect of what if everyone in the population had gotten it versus nobody. But a quantity that is frequently targeted is the effect of treatment on the treated. So in people who actually received treatment, what was the average effect? So for kind of program evaluation, was it worth it for the people who did it? That can often be a question, as opposed to maybe a policy question, which is, should we do this for everybody, when maybe the average treatment effect would be of more interest? And this is just a special example of a subgroup effect. It's the effect in people who actually did receive treatment. And the way to estimate this is you fit the model for the outcome to the whole population. But then when you're doing standardization, you just, again, restrict to the people, to the treated group, just like any other subgroup analysis. Okay, so let's do this in R. So we'll start by reading in that NHAFS data set again. And the first step is to fit the regression model, weight gain from 71 to 82 as a function of the treatment, quitting smoking, and a bunch of covariate, and also including an interaction between treatment and smoking intensity in 71. Okay, so the model is fit. Here are all the coefficient estimates. But now let's say we want to limit this to a particular subgroup. We're going to do standardization, but we're going to restrict it to rows where the sex variable takes a certain value. I think it was 0 as men, one is women. So here's how we do that. We're going to create a copy of the original data set, which is NHEFs, but we're going to restrict it. We're going to subset it to rows where the sex column equals 0. So I think that's men. Okay. So now we'll set everyone's treatment value in that data set to be 0. And we'll predict what their outcome under no treatment is. And then we'll do the same thing, but we'll set the treatment value to be 1. So again, the original data set restricted to men, but then setting the treatment value to be 1 and predicting everybody's outcome had they been treated. So then the average weight gain under treatment, like under quitting smoking in men, was 5.3 pounds. Had all men quit smoking, the average weight gain is estimated to be 5.3. And had no men quit smoking, the average weight gain is estimated to be 1.7. And so the conditional average treatment effect, the CATE in this group in men, is just the difference of these means, and it's 3.6. We can do the same exact thing for women. I'm not going to go through every step slowly. I'm just going to highlight it all and run it because it's the exact same thing, except we're just restricting to sex equals 1 instead of sex equals 0. The effect estimate is 3.4. So for women, it was 3.4, and for men, it was 3.64. And so that's a 0.15 difference. Keep in mind, there's this difference of 0.25 pounds between the two subgroups, and later we'll bootstrap to find the standard error of that difference between the effects in the two subgroups to see if there's actually a statistically significant difference in the effect of quitting smoking on weight gain between men and women. But first we'll do effective treatment on the treated. So here we're going to do the same thing, but we're just going to restrict the data set to where the treatment value is 1 to the treated. And we're going to set everyone's treatment value to be 0, even though in reality it was 1 for everyone in that data set, and predict what their untreated outcomes would have been. And then we're going to do the same thing. We don't need to set their treatments to be 1 because they're already 1. We're restricting to the treated. And we'll, again, just get their model predicted outcomes, but you could also just use their real outcomes because they were treated, all of them. The mean weight gain in the treated, had they all been treated, which they were, 4.35. And the estimated mean weight gain in people who quit smoking, had they not quit smoking. So effective treatment in the treated is just the average effect over everyone, men and women, in people who actually receive treatment. So here's the mean weight gain under the treatment they actually received, which was like quitting smoking. And here's the estimated counterfactual weight gain that they would have had none of them quit smoking. And here's the effective treatment on the treated, which is just the difference of those two. So 3.4. So that's the effective treatment on the treated, which is like a very commonly targeted, what's called an estimand, like quantity of interest. A lot of people are interested in that to just see what the effect was, again, on the people who actually received the treatment. Okay, so now what we're going to do is we're going to go back to that difference in the estimated subgroup effects in men and in women, and we're going to check if that's statistically significant using Bootstrap. Something to note, we didn't have an interaction in our model between sex and treatment, but it could still be the case, for example, that men are more likely to be intense smokers than women, or vice versa, right? And we did have an interaction with smoking intensity. So for that reason, you could still have a different effect in these two subgroups. So let's check if it's statistically significant. We're going to do 500 bootstrap samples. We're going to make an empty vector to store all of our estimates of the effect in men, make a separate vector, empty vector, to store all of our estimates of the effect in women. And then we're going to have a for loop where for each iteration of the for loop, we make a new data set, a bootstrap data set, resampled from the original, and we fit a model, and then we just do exactly what we did outside of the bootstrap. In this section of code, it's the same thing as before, but just with the bootstrap data set. We estimate the effect of quitting smoking in men and then store it in that vector. And then we estimate the effect in women and store it in the vector. So I'll just run the for loop. Here's the histogram of the effect estimates in women and the histogram of the effect estimates in men. And here's the histogram of the differences in the effect estimates. And you can see just from looking at this that it's not statistically significant, right? That a pretty sizable proportion of the estimates are greater than 0 and also less than 0. There's not a lot of certainty about the sign of the difference of the effect in men and women. But let's just continue to go through the process. And there is our point estimate of negative 0.25, which is like pretty much in the middle of the bootstrap distribution, which is as it should be. So let's just keep going through the process of making a confidence interval for the difference in the subgroup effects between men and women. So to get the standard error for the difference, you just take the standard deviation of the vector of the 500 differences, which is all the effect in women estimates minus all the effect in men estimates. Just take the standard deviation of that. It's 0.22. Here's the point estimate that we originally got, that original difference in the two effect estimates is negative 0.25. And so we could get the upper bound on the confidence interval by taking that point estimate and adding 1.96 times the standard error. And so the upper bound is 0.19 on the other side of 0 from the point estimate. So we're not confident about the sign. And then we can get the lower bound by subtracting 1.96 times the standard error from the point estimate. So our confidence interval for the difference in the effect of quitting smoking on weight gain in men and women is negative 0.68 to positive 0.19. Let's talk about using causal graphs to determine whether exchangeability holds. So like whether it's allowed to do causal inference and what to adjust for to make sure that it is allowed. The first question is, when does exchangeability hold, or what is exchangeability given covariates, right? Exchangeability holds if within levels of covariates, that means if you fix the covariates, you look at only people with a particular value of the covariates, the treated and untreated don't vary systematically in ways that are associated with the outcome. So if you fix the values of the covariates, then you can just compare the outcomes in the treated and the untreated in people who have that value of the covariates. And that will be the causal effect of treatment in that group, in the group of people with those covariate values. So here are 3 examples where exchangeability does hold. I'm going to describe the 3 examples with graphs, and we'll also just try to see why it's the case that this other kind of definition of exchangeability holds if these graphs hold. So the first is a randomized experiment. So there are no common causes of the treatment and the outcome in a randomized experiment, because the only thing that determines treatment is a coin flip. So nothing else can cause it. So that means in a randomized experiment that the treated and untreated will not vary systematically in any way, let alone in a way that would be associated with the outcome, right? So exchangeability holds in this case. Here's another case, the simplest confounding scenario, where you just have a common cause of A and Y, of treatment and outcome. So let's say L is binary, it's just 0 or 1. If you fix L to be 1, you're only looking at the people with L equals 1. Then there's no other common cause of A and Y in the L equals 1 group, right? Because L is the only thing on this graph. So within the L equals 1 group, the treated and untreated A's don't vary systematically from each other on any other variable that's associated with Y. And so exchangeability holds conditional on L. And L is how severe your headache was before you either did or didn't take aspirin. So if the only thing that both impacts whether you take aspirin and whether you still have a headache is the severity of your headache initially, then if you limit it to just the severe headache people, there's nothing else that will make the aspirin takers and the non-aspirin takers within the severe headache people different from each other in ways that are also associated with the outcome. Like if you're only looking at the severe headache people and severe headache is the only common cause, then there's no other systematic difference in the treated and untreated. And so that's why exchangeability holds, and why within each level of L, it's like you're in a randomized experiment. You can just take the difference between the mean outcome in the treated and the untreated, and that's the effect of treatment in people with that value of L. And here's a slightly weirder one. Let's say there's some unobserved covariate U, which causes A, the treatment, and there's a measured covariate L, and U only influences the outcome through L. So now let's fix L to be 1. So we're only looking at the L equals 1 people. The treated and untreated people will now differ in their U values, definitely, right? Because U causes A. But since U only causes Y through L, and we're fixing L, then the treated and untreated's difference in U has no impact on Y, because everyone has L equals 1. The only way U influences Y is by changing L, and we're just fixing L. We're only looking at the people who have L equals 1. So again, we're in a situation where there are no systematic differences between the treated and the untreated that are also associated with Y in people with any given fixed value of the covariate L. So these were 3 examples where exchangeability holds. So let's generalize. Instead of looking at a graph and trying to just reason, should there be no systematic differences between treated and untreated, you can actually just look at the graph and apply a rule, and you can know whether it would be the case that exchangeability holds and there are no systematic differences between treated and untreated. And it's called the backdoor criterion. Okay, so a backdoor path between A and Y is a non-causal path, so not due to the causal effect of A and Y, that remains even if all arrows pointing out of A are removed. So there are no backdoor paths in this bottom left graph, right? Because you remove the arrows pointing out of A and there are just no arrows left. Nothing connects A and Y. So in this simple randomized experiment example, there are no backdoor paths. In this example, L, which is a common cause of A and Y, it has an arrow pointing into A, which would remain if you take the arrows away, the arrows pointing out of A. So this path A to L to Y is a backdoor path, and same with A to L to U to Y. So there are 2 backdoor paths between A and Y in this graph. And then here, again, you take out the arrows pointing out of A to Y, there's a backdoor path A to U to L to Y. So here's the backdoor path criterion. If all backdoor paths between A and Y are blocked by non-descendants of A, meaning something that doesn't have a sequence of arrows, A points to something, points to that, or there are no backdoor paths, like in this simple example, then exchangeability holds. And that means it holds conditional on those blocking variables. So for example, here L, if you condition on L, you block all the backdoor paths between A and Y in this graph. ALY blocked, right? ALUY blocked by conditioning on L. You can think of it as backdoor paths induce associations between A and Y that are spurious, like they're not from the causal effect of A and Y. And if you block all of those, if you condition on all of those, then the only remaining association between A and Y is going to be due to the causal effect of A on Y. Now, just to define blocked, a path is blocked if you adjust for a covariate on the path that's not what's called a collider. So here L is not a collider. A collider is something that has arrows coming into it from either side, from both sides. So if you adjust for L, you block this path. If there is a collider and you don't adjust for it or you condition on it, then you also block the path. So that's all there is to it. If you have a causal graph and you can find all the backdoor paths between the treatment and the outcome, and you choose a set of variables to condition on that blocks all the backdoor paths, and make sure you don't condition on colliders to open up paths, then you're good. I have two examples of colliders here. Whether your car has an ignition problem and whether its battery is dead are totally independent events normally. But given that your car won't start, and forgive me if this makes no sense because I don't know anything about cars, but it sounds good to me. If your car won't start, then, and that there's an ignition problem, you wouldn't think there's also a battery problem, right? So, oh, that explains it, explaining away. And that means that given that it won't start, ignition problem and battery problem are associated. But ordinarily, they're just totally independent processes. But once you see that it won't start and you understand, you have this clear reason why it wouldn't, it makes it less likely that there's also a battery problem at that exact moment, right? Similarly, if you see that someone got into Harvard, for example, and you know that they got great grades, you think, okay, less likely to be a legacy, right? But if you see that someone got into Harvard and they have horrible grades, you think, oh, they must be a legacy. But if you don't condition on getting into Harvard, getting great grades and being a legacy are maybe independent, maybe not, but pretend they are, they could be. But then only once you condition on this collider, this thing that they both might be causes of, do they become associated. Another example would be someone's in the NBA, that they're 7 feet tall. They're less likely to be a great shooter once you see that they're 7 feet tall, because that's another way to get into the NBA, just being really tall. Or if you hear that they're a great shooter, then it's not so likely that they're 7 feet tall because they don't need to be 7 feet tall to get into the NBA if they're a great shooter. There are tons of examples explaining away. So that's how, in general, conditioning on something that's a collider can induce an association between the two things with arrows pointing into it. So here's a very simple example. You have A, Y, treatment outcome. Here's a covariate L that you might be tempted to adjust for. If you adjusted for it, you would open up the backdoor path A to U2 to L to U1 to Y, because L is a collider. So through that explaining away process, when you condition on L, it also becomes associated with U1 through explaining away, examples of which we just saw, and U1 is associated with Y. So now you have this path of association between A and Y that has nothing to do with the causal effect of A on Y. So you're going to get a biased estimate of the effect of A on Y because you adjusted for L, which opened up this backdoor path. So you can actually adjust for too many variables. You can induce various associations by adjusting. It can still be a good rule of thumb when in doubt, adjust, but it's not ironclad. Here's an example where you're damned if you do, damned if you don't. If you adjust for L, this is the same example as before, you open up this backdoor path, A to U2 to L to U1 to Y, right? But if you don't adjust for L, then this backdoor path, A to L to U1 to Y, is open. So whether or not you adjust for L, there's going to be some backdoor path open. So the estimate of the effect of A on Y is going to be biased because you can't close all the backdoor paths. But if you could observe L1, then you could block all backdoor paths by adjusting for L1. If you don't adjust for L, then this backdoor path is closed because it's a collider that you're not conditioning on. So you can't get from A to Y this way. And if you try to get there this way, you get blocked by conditioning on L1. So if you condition on L1, you block all the backdoor paths between A and Y. And so it suffices to adjust for L1, basically put it in your regression and do standardization, and you'll get an unbiased estimate of the effect of A on Y. So then you can do standardization, which is taking the average of the effects of A on Y over all the values of L1, that weighted average. So if it's true that if you condition on L1 that just those naive comparisons of the difference in the expected value of Y given A equals 1 and A equals 0 is actually the effect of A in that value of L1, if that's true, then you can just do standardization to get the average effect. It means that we can do everything that we've been doing in class with L1 as our covariate and get the average effect of A on Y. So with this background of what's necessary for associations to be causal and how it's possible to have spurious associations, I want to talk about how to be a more discerning consumer of regressions. A lot of the time, you'll see papers, often they'll be highlighted in the media, that are basically the result of throwing a whole bunch of variables into a regression with kind of no regard for what the causal interactions between all the variables are, like what the causal graph is that describes their relationships to each other. And people will try to interpret many different coefficients from models like this, or sometimes they'll have one of interest, but the regression that they specified to try to estimate its effect really makes no sense if you think about what the likely causal structure connecting all the variables is. So I'm going to go through two examples of regressions like this. The first is a critique by this guy, Clark Lymore, who was the pioneer of causal graphs and how to reason with them. A critique of the bell curve, which is like a notorious book trying to argue that IQ is behind everything. And the other study that we'll look at is this paper that got highlighted prominently recently in the New York Times, and basically every media outlet covered it, showing that economic connectedness is a big driver of social mobility. So first, the bell curve critiques. It's by this guy, Charles Murray. And again, his whole thing is trying to show that IQ is extremely important for causing all sorts of outcomes using regression analyses. Here's his model of the world, or a model of the world in which his regressions might make sense. IQ is a measure of cognitive ability. There's this measure of socioeconomic status index, which is driven by properties of the parents. And these things are assumed to also cause the outcome of interest X. And then there are other confounders, Z, which are associated with the socioeconomic status variables and also cognitive ability and also X. And here's a simplified version that assumes that the crude measurements of variables are the variables themselves. So this undirected arrow means that these are associated through maybe a common cause, not that one actually causes the other directly. And same here, wherever there's an undirected arrow. And so Murray takes an outcome of interest X, maybe like income or something, and regresses it on IQ score, socioeconomic index, and Z, like age, stuff like that, and tries to interpret the resulting high coefficient of IQ as causal. So the first obvious criticism of this approach is that there could very easily be unmeasured common causes like W here. Everything in a circle is unmeasured common causes of IQ score and the outcome, right? And if there were such a variable, that would be a backdoor path. And so the regression that just adjusts for socioeconomic status and Z would not yield an unbiased effect estimate. Another possible critique, which again seems quite likely, is that there are unmeasured common causes of IQ score, the treatment, and the socioeconomic status index, and then also of the socioeconomic status index and the outcome of interest. And this is that M bias situation from earlier, right? Or the damned if you do, damned if you don't situation, where if you then adjust for socioeconomic status index, you're inducing an association between treatment and the outcome that's non-causal. And again, you'd get a biased estimate of the treatment effect. It seems very hard to rule out something like this, and it seems quite likely that this would be the case. Yeah, Murray did this both with and without adjusting for education. But when he conditioned on education, like doing the analysis within levels of educational attainment, he reasoned that this conditioning blocked that IQ actually caused education, which caused the outcome. And that conditioning on it blocked this path and left you only with the direct effect of IQ on the outcome, not through education. But again, this reasoning would only hold if there weren't a variable like U, which again opens up this backdoor path where if you condition on education, you have IQ to education to U to X. And of course, there are going to be unobserved common causes of education and pretty much any outcome that weren't in the model. So again, by conditioning, you'd induce an association. So it's basically a hopeless endeavor. Using regression, establish causal relationships between something like IQ and life outcomes. So that's Glymore's critique. And I think maybe it's kind of easy to get behind because, at least for people who aren't fans of what Murray is saying, it's easy to see why this should be wrong. But tons of social science does similar things. So here's an example of a paper, the one I was describing about social mobility and whether economic connectedness, which is this construct summarizing how many higher socioeconomic status friends people tend to have, and whether that's a driver of social mobility. So here's a plot at the county level of economic connectedness, like averaged over people in the county, and the social mobility in the county as measured by the predicted household income rank for children with parents who are at the 25th income percentile. So San Francisco has pretty good mobility here, as the highest economic connectedness, and pretty good mobility. Yeah, you're expected to be at the 50th if your parents were at the 25th. This establishes an association, and they want to know, is this causal? And what they say in the paper, the way they try to get at this is, when we regress measures of upward mobility on standardized versions of all of the social capital measures together, economic connectedness remains the strongest predictor of upward mobility by a significant margin. By contrast, measures of civic engagement and network connectedness have coefficients near zero. They did a regression suit where they threw in the thing that they're considering their treatment, which is economic connectedness. These are like coefficients in their regression on the x-axis. So it had a big coefficient. So that means that they want you to interpret this as economic connectedness is causing social mobility, which is the outcome of the regression that they fit. But they just threw in a whole bunch of other covariates to this regression. It's hard to imagine what the causal graph could even possibly look like here. What comes after what on the causal path? Are you adjusting for things that economic connectedness also causes? There must be unobserved common causes of most of these things in the outcome. Surely there are other common causes of economic connectedness in the outcome other than these things. So it feels suggestive in an informal sense because there's a strong association before adjusting for things and there's still a strong association. But you could say Murray's analyses are suggestive by the same criteria. So I'm not sure they're the criteria you'd want to apply. It's interesting that there is this construct that seems to be strongly associated with an outcome, and you could tell a good story about how they might be causally connected. But at the same time, it's a regression soup, right? It's just throwing a bunch of variables in, and that can induce all sorts of spurious associations and fail to block all sorts of backdoor paths, and it's hard to interpret this as causal. Another screed against regression soup, there's a link to a paper that goes into this in depth by Greenland and Weisstreich. They call it the table 2 fallacy. So very often in research papers that use regression to estimate an effect, Table 1 will give summaries of the covariates in the treated and untreated. That's like classic Table 1 in a paper. And Table 2 will often just give coefficients of every variable that was included in the regression, whose purpose was really just to estimate a treatment effect. And their point is that it's very difficult to interpret the coefficients of covariates that weren't treatment. Like treatment is special because, at least ideally, the other covariates were chosen such that they preceded treatment temporarily and blocked the backdoor paths between treatment and the outcome so that you can interpret its coefficient in a causal way. That's not true for any of the other covariates. There are presumably common causes between them and the outcome, but they might be in any temporal ordering. Some of them might cause others of them, so you're like blocking part of their effect, and it's just basically impossible to interpret their covariates in any coherent way. The coefficients can switch sign and change magnitude greatly depending on what other variables you throw into the model. And even though that's the case, like if people try to interpret the coefficients, it's rarely in a way that's tailored to what other covariates are in the model. For example, taking the Chetty paper, you could say, I know EC was their treatment, but we described how it wasn't based on any DAG, so I just used it as the example. The expected difference in social mobility between two counties with EC differing by 1 and the same age connectedness, clustering, and civic engagement scores, that's how you'd interpret the coefficient of a regression that had these 3 covariates in addition to EC. That coefficient might be totally different, like totally other direction from the expected difference. The coefficient can change sign, it can change magnitude for almost completely incomprehensible reasons. So here's the abstract of their paper, and it just says, like what I just said, it is common to present multiple adjusted effect estimates from a single model and a single table. This can lead to mistaken interpretations of these estimates. They use causal diagrams to explain why. Presentation of exposure and confounder effect estimates from a single model may lead to several interpretive difficulties, inviting confusion, blah, blah, blah. Okay, there's this other paper, which seems to be like exactly the same, which just was updated. Control variables are included in regression analyses to estimate the causal effect of a treatment on an outcome. In this article, we argue that the estimated effect sizes of control variables are unlikely to have a causal interpretation themselves, though. This is because even valid controls, so now some econ jargon, are possibly endogenous. That means there are common causes of them in the outcome, and therefore represent a combination of several different causal mechanisms operating jointly on the outcome, which is hard to interpret theoretically. And so again, they say basically just don't include those effect coefficient estimates in papers. I guess that's the end of that kind of sermon on how hard it is to interpret regression coefficients that are not the coefficient of a treatment in a multivariate regression. I do think it's important to being like a good regression consumer to have the term table 2 fallacy, which is used a lot by epidemiologists to describe that kind of mistake. Now we're gonna switch gears a little bit and talk about regression to analyze randomized experiments. The whole rest of this class, we were talking about using regression to get rid of confounding, but in randomized experiments, there is no confounding. Like when you flip a coin, you break any relationship between either measured or unmeasured variables and the treatment. So there can't be any common causes of treatment and outcome or any backdoor paths. Nothing can have an arrow into treatment. So there are no backdoor paths in a randomized experiment. So here's an example of a big RCT, thrombolytic therapy versus primary percutaneous coronary intervention for myocardial infarction in patients presenting to hospitals without on-site cardiac surgery. So just comparing these 2 treatments for heart attacks. And here's the table 1. There's no table 1 fallacy. So here's table 1, where they typically compare the treated and the untreated groups. And you can see that through the miracle of randomization, most of these covariates are very close to each other in mean across the treated and untreated arms. There will be chance imbalances, but mostly they're similar. And the bigger the randomized experiment, the more similar they'll be. There are some chance imbalances like hypertension, 43% in the thrombolytic arm versus 51% in the primary PCI arm, or I guess 135 to 140 is a sizable difference in average blood pressure in the 2 groups. So there are chance imbalances. RCTs are unconfounded, so you can just estimate the treatment effect using a very simple linear model where you just regress the outcome on the treatment and no covariates. and it won't be biased. You're safe doing this. This is fine. Just doing an unadjusted comparison of outcomes between treated and untreated groups in RCT is fine. But RCTs do collect information on baseline covariates that they think are important for the outcome, and they make that table 1, and it's available to statisticians who are analyzing data from an RCT. And there are sometimes chance imbalances between treated and untreated groups. So you could and should actually, if you're analyzing data from an RCT, you should actually use a linear model. Let's say it's a continuous outcome. You should use a linear model that regresses on treatment and covariates, and you don't even need to use interactions. Don't use interactions, and take the coefficient of A as the effect estimate. And if you do that, you're still going to get a valid, meaning unbiased estimate of the treatment effect, even if this model is not correctly specified, meaning even if there are like lots of interactions, and really you should be using like transformations of the variables like squares and logs and whatever. So even if the model's wrong, if you fit it, you still get a valid effect estimate for A in beta 1. And it also usually reduces the variance of that estimate. So you get a more precise estimate. You're confident it's in a narrower range than if you just do the unadjusted version, especially if the L covariates are strong predictors of the outcome. So it's important to specify in advance, like in your analysis plan, which covariates you're going to adjust for in a model like this. Otherwise, p-hacking is a concern because the results can change slightly depending on which covariates you adjust for, and someone who's motivated to get a statistically significant estimate of beta 1 can try all sorts of different covariates to adjust for until they get one, if they're borderline, let's say. So you should specify in advance which ones you're going to use, and in choosing which ones you're going to use, you should pick the ones that you think are most predictive of the outcome. And you shouldn't pick too many, because if you pick too many covariates, then you won't actually reduce the variance. So pick just a few and the ones that are most strongly associated with the outcome. This reduces variance because it partially corrects for chance imbalances in the covariates that might arise even with randomization. So you might also wonder like why you don't even need to have the right model, and also why you don't need to standardize the way we've had to standardize in the past. And it's because anyone can ignore this math who wants to, but if you're interested, beta 1, which is the coefficient of A in that regression, is a weighted average of the effects of A across strata. And the weights are given here. And you can see that there are these probability that A equals 1 given the value of the covariates terms. And if you have a randomized experiment, these are just all constants. It's just 1/2. It doesn't matter what the covariates are because you were randomized, right? So these can all be like removed from the weights if the data come from a randomized experiment. And then you're just left with the weighted average of the treatment effect given the covariates weighted by the prevalence of that covariate value, which is the correct standardization weight that we've seen before. So in a randomized experiment, by magic, the regression weights that were usually wrong and that motivate us to do standardization in observational studies, you don't need to standardize if the data come from a randomized trial. I've meant to add another slide about another reason that you might want to use regression when analyzing a randomized trial. And I'll add the slide later, but I'll just talk about it a little bit right now. And that reason is to estimate interactions between the treatment and covariates. And that's to get a sense of how the effect varies depending on what the values of the covariates are. So to get subgroup effects, essentially. That's another thing you can use regression for if you're analyzing data from an RCT.